For some 50 years, Dr. John Mather has had a unique perch on the universe, first via NASA's Cosmic Background Explorer mission, or COBE mission, that he led from 1974, and then the revolutionary James Webb Space Telescope from 1995. Along the way, he has made many pioneering contributions to space science, as well as won many awards and honors, including the 2006 Nobel Prize for Physics, along with Dr. George F. Smoot of the University of California for their work using the COBE satellite to measure the heat radiation from the Big Bang. At 77, Dr. Mather remains deeply engaged with his scientific passions that dwell in the realm that is often billions of years old and parsecs away in the universe. He spoke to Mayankshire Reports on the exciting and breathtaking findings of the James Webb Telescope, whether they append the Big Bang Theory, the age of the universe, quantum mechanics, and more. Dr. John Mather. I know it's a bit late to congratulate you on your 2006 Nobel Prize, but you dwell in a realm where years are measured in billions and distances in parsecs. So, congratulations.
Thank you. It's a great honor for us and for our whole team that did that project.
Indeed, indeed. The James Webb Space Telescope was launched almost exactly 2 years ago, to be precise, December 25th, 2021. Give us a broad overview of how it has been throwing so many curveballs at the physics community about the universe.
We set off to observe what had never been observable before, namely infrared light from the most distant universe, from inside dust clouds where stars are being born, from distant planets where we can see their atmospheres in ways we never could see before. So we are thrilled that the telescope is working so beautifully. I guess everyone saw the launch. As you mentioned, it was a perfect launch. The first great surprise was that the equipment worked so beautifully. Everything went like clockwork as we unfolded it in space. And then we started right off to observe the program we had planned many years in advance, looking at the first stars, the first galaxies, the first black holes, stars being born inside their dusty clouds here close by, and exoplanets. As you know, we can see exoplanets not directly, but when they pass in front of their stars. So when they do that, we can examine their atmospheres because some starlight goes through the planetary atmosphere on its way to a telescope. So we've basically shown, not that was so much of a surprise, but that the technique works very well. We can see remarkable numbers of different molecules in large planets. We've seen sodium and potassium and water and ammonia and sulfur dioxide and carbon dioxide in large planets. And it's perhaps a disappointment, but not a surprise, that none of the small Earth-sized planets yet seem to have an atmosphere. We were not surprised by that because the only targets we can look at with this technique are orbiting rather hostile stars called M stars. So that is not a big surprise, but we're still pleased that the technique is working.
Do you think there is enough realization outside the scientific community how astonishing this achievement is, to have something as sophisticated as this flying around at 1 million miles from us and producing such breathtaking images?
Well, I don't know how much the rest of the world knows what it took to build the observatory. But when I tell the story, I say, well, you know, I joined the project in 1995 and people already were planning ahead years before that. And it ended up taking 20,000 people and about 10 billion US dollars plus contributions from Europe and Canada. And just an immense effort because we needed a telescope that was very different from anything ever built before. What's different is it's much bigger. So it's so big that it will not even fit into the rocket without being folded up. It is much colder. So unlike the Hubble telescope, which operates around the temperature of our household, or what we call room temperature, this one is cooled down to about 40 degrees above absolute zero. So that means a completely different design. It means it cannot possibly be done near to Earth because otherwise it would be warmed up by the Earth. Just a dramatically different mechanical and optical concept is required to do this. And the upshot is an extremely complex system that has to unfold after launch, and many ways that it could have gone wrong, but did not. So we were so pleased that our efforts worked. Of course, how do you know that it's going to work? You have to practice. So we tested many times with unfolding the observatory in laboratory here on the ground. And still, there's always a little bit of worry because what if there's something that we didn't think about? And but we thought of enough of everything so that it works. Yes.
One of the biggest surprises has been the discovery of, and I'm hoping I'm pronouncing the name right, the Maisie's galaxy, which existed barely 390 million years after the universe was apparently formed. And it's considered that it poses a serious challenge to the way we understand galaxy formation, and not just that, but beyond that, even the way the universe is. What's your take on that?
Well, it seems to me the most likely challenge is explained by we don't know how galaxies grow. The idea that the whole story of the expanding universe is incorrect, well, that's pretty unlikely because we have so much evidence over so many decades that it's true. But the details of how a star is born are all different back in those early times. The density of the universe was 10,000 times higher than it is now. Magnetic fields were different, temperatures were different, everything was so different. The chemical composition was different. In those early times, the gaseous material was only hydrogen and helium as given us from the Big Bang. And recently, when we see stars being born close by, they're made out of hydrogen, helium, and many chemical elements like carbon and oxygen and nitrogen, and iron and phosphorus and sulfur and the other kinds of things that we see around. So we know that it should be different. What we don't know is how to predict it. So our inability to predict is not really a big surprise.
I see. But the fact that this galaxy, the 390 million years old, born after that amount of time, it's almost like a baby being born with a fully grown beard. Isn't that isn't that
Well,
strange that it's so mature so
yeah,
early?
people are surprised by that. But I think it's we just don't understand early things happening. The basic idea that people have is expanding universe is not exactly homogeneous. There are hot and cold spots that we saw in the Big Bang in the heat radiation, and that's why we got a Nobel Prize, for instance, back in 2006. They tell us that because the early universe was not homogeneous, there were places that are a little more dense than average. And when there's a very unusual, very dense extra density, an overdensity, we call it, it's able to stop the expansion sooner, and the material will be pulled back in by gravity to make a new something. And then when we know that that's happening, then it's suddenly all different because we don't know the details of how something can grow. We just know something is going to grow. So
Right.
suddenly, a very unusual event is happening, and we feel very lucky to be able to even find them because they are rare. And so to find them, we have to look at a lot of different places in the sky and recognize a telltale sign that something is special about that object so that we can then follow it up. So the way that we find them, by the way, is we take pictures with the near-infrared camera, and then we look for objects which have infrared light but no short wavelength light. And the reason that this is important is it's a sign that all the short wavelengths have been absorbed by intergalactic hydrogen. In hydrogen, all the wavelengths that are shorter than a certain number are able to pop an electron out of the hydrogen atom and be absorbed. So That means the intergalactic material is opaque for certain short wavelengths. And then we look for the sign of this in the colors of the distant object. Then when we see such a thing, we say, then we better follow it up with a spectrometer, and that means we spread out the light into a rainbow and look to see, does it have this telltale shape? And also, does it have any sign of any particular atom or molecule that might be telling us about the conditions in that object? So that's what we're doing to find these very distant objects. And then we also look to see, well, how hot are they? What's the temperature? How are they moving? Are they alone? And so there's a lot to follow up once you find an interesting object.
I see. How do you see something, a star like, say, Methuselah, which appears to be older than the universe?
We figure that's a mistaken calculation.
I see. I mean, it's as simple as that, is it?
Yeah. So with the age of the universe is very well understood. So we've known about the expanding universe since 1929, when Edwin Hubble drew us a graph showing the distance of galaxies versus the speed at which they're going away. You divide the distance by the speed, and you get the apparent age of the universe. And you can make a small mistake or a large mistake, but we've had a lot of time to correct those mistakes. So we're now down to uncertainty of around 10% at best. So that's significant and interesting. But when you see a star that seems to be older than the universe, well, you just don't know how to figure out the age of a star,
Okay.
And you look at a luminous object, a little point in space, and you say, well, how old are you? And you have to have a story about how did that star grow? How does it get older? What are the signs of its age? So here locally, we can calculate the ages of stars by comparing them with their neighbors and with the calculations we have about the nuclear physics inside of a star. How fast does the star burn up? It's the hydrogen fuel and all of those things. So we got a pretty good understanding of things locally. When we look at very distant objects, they're all different, and we don't have very much to go on.
In that context, how do you see a paper by University of Ottawa Professor Rajendra Gupta, I'm presuming you're aware of it, where he revised the age to be 26.7 billion years old, the universe's age. And he has gone into the question of twilight, redshift, etc. How do you look at a claim like that?
Yeah, well, he's certainly got a very minority viewpoint. I think almost nobody else is convinced by his story.
Okay. Do you believe that the JWST findings may begin to challenge the long-held Big Bang theory?
Really not. Everything we've seen so far says the expanding universe, Big Bang story is correct. We are working on the details, but the general idea is correct as far as we can tell. So what could be interesting and different? Well, there are quite a few interesting subjects of the expanding universe story that are mysterious. One is that astronomers calculate that there must be something called dark matter. And we know it's there. It has gravity. It affects the motions of things. It affects the temperatures of things. It affects the formation of galaxies. And it's invisible. It's transparent. There's something we call dark energy, which says that the universe is not only expanding, but accelerating. That was definitely not predicted by very many people, if any. When we observed that, it was such a big surprise that people got a Nobel Prize for discovering it. There is no fundamental understanding of that one either. The current big mystery that we're working on is that there are multiple ways to estimate the expansion rate and hence the age of the universe. And they disagree by what we call 5 sigma. That is to say, there's a very small chance that this is a randomly occurring error in observation. There's something else going on. So either we have made a mistake, or nature has fooled us, or there's something really interesting happening. And so we're going to be pursuing that one for quite a while.
I see.
Nobody has found any mistakes.
Okay.
So that
Rich,
means really interesting.
recently, I had an extended interview with Dr. Chandra Wickramasinghe, who is an associate of Sir Fred Hoyle, the proponent of the steady state theory.
Oh, yes,
Uh,
yes. Very famous.
I know the steady staters have taken a beating, but Dr. Wickramasinghe continues to believe that the Big Bang would have been sort of a local phenomenon in an overall steady state. Do you think that's a possibility?
Well, I don't think so. It seemed to me that the way you just described it is not the way I was thinking about it before. Well, the steady state theory used to talk about the whole universe as a whole being replenished by creation of matter. And so it only would seem to have an age. Um, their idea was the age was actually infinity, um,
Right.
and that and their answer to the puzzle was to create matter to replace the expanding, diluting material. So the problem with that story was they never did predict correctly the spectrum of the cosmic microwave background radiation, which we measured so precisely with the Cosmic Background Explorer satellite.
Right.
So since they couldn't predict that, it sort of got a lot less interesting.
Right. And the irony is that Fred Hoyle used the term the Big Bang Theory, coined it as a sort of a derisive, dismissive term about the Big Bang, I mean, with the prevailing theory of that day.
Yes, people say that about him, but he actually denied that he was trying to be derisive. He said it was
Okay.
just something that came up in a conversation on the radio,
Okay.
And
Uh,
curiously enough, he doesn't really get enough credit for having done some really original work on something that resembled the Big Bang, um, but was not called the Big Bang.
right.
So when I was a postdoc and working on the idea of the Cosmic Background Explorer satellite, I came across a paper that Fred wrote on how a variable mass field would behave. And if the properties of all the elementary particles were proportional to this particular imaginary quantum field, then it would look like the Big Bang.
I
And
see.
people have ignored this fact and thought, well, Fred didn't like the Big Bang, but it actually was in his paper that something could resemble it very well. So um, anyway,
Yeah.
he was a very wonderfully creative man, and I respect him immensely.
Speaking of wonderfully creative, let me bring in another voice. Roger Penrose has been talking about conformal cyclic cosmology, the idea that the universe has always existed but goes through cycles. How do you view that?
Well, I think I'm not convinced one way or the other. Anyway, as far as I'm aware, there is no evidence that we have of previous cycles. The conditions in what we call the Big Bang are so extreme as to erase almost all the details of what came before. So you have to work really hard to find any sign of evidence of the previous cycles. But it's certainly a plausible idea in the sense that, well, the way I look at it, when we imagine back in time to when the conditions were hotter and denser and hotter and denser and hotter and denser, eventually we say we have no idea what's going on. The laws of nature that we know now ought to be wrong. So when they ought to be wrong, then what? So we're pretty much guessing. So I think there's space for a cyclic universe, but I don't know if there will ever be a proper observational test.
I see. So, I mean, you're not. It's for you. It's not something that you dismiss it completely because Roger Penrose has prompted a lot of negative reaction to his theory.
Yeah. So a harder question is to ask: is there actually any evidence?
Right. Right.
And so, where do you look for evidence? One place you can look is in the pattern of spots in the microwave background radiation, the hot and cold spots. And if you find patterns there that you think are unlikely in the current picture of the expanding universe, then you say, well, maybe they're left over from something before.
I see.
I know he's been thinking about that. I don't know what the current arguments are, but I
Right.
know interpreting the numbers that we have is always tricky. We only have the one universe to look at, so
True.
we have what the astronomers call cosmic variance. In other words, we know that we can only look at our particular small piece of the universe, which we imagine is infinite. And so we don't know whether our piece of the universe is representative of the whole thing.
I see. Yeah. To change gears a bit, one permanent feature of the universe is that there can never be real time communication between bodies given the limitation imposed by the speed of light. How do you, as a physicist, view the fact that we are forever trapped in a huge datedness in data and information exchange, which seems impossible to overcome?
Well, I'm not sure what your question is about, but I know the one of the strongest ideas of explaining the universe that we have is called inflation theory, which is a hypothetical quantum mechanical field that would cause the accelerated expansion of the very early universe. And that would imagine that there was something more or less static, which then became unstable and turned into the universe that we have. So that would explain why people or places that have never been in what we call causal contact since the expansion began could look so similar. So we say, well, they were in contact in the very earliest moments, and then they were spread apart. So that's the kind of evidence for the inflationary theory of the early universe. It's
I
a
see.
it's a part of the expanding universe story. It does not challenge the Big Bang story. It's just a part of it.
Yes, no, my drift was a little more philosophical in the sense that we are never able to communicate in real time over long distances, given the speed of light limitation. Uh, with that being the case, it's a fact that we will always remain dated in our information exchange. Is that something that troubles you as a physicist?
No, it would surprise me if there were any alternative.
Okay, okay. Another point I wanted to raise with you is the definition of a year, which is ours is an anthropocentric, Earth-specific definition of a year. Imagine on the Kardashev scale, there is an exoplanet, which is very similar to us with Type 1 civilization. They may have a completely different definition of a year, and they may define the universe very differently. How do we reconcile? I know this is rather hypothetical, but I'm interested to know your view on that.
Well, I don't know exactly what the differences could be. We, as scientists, we can only make sense of something that's about the same everywhere. We say, well, our laws of nature they're not really laws of nature unless they apply everywhere.
Right.
So, so the in a way, the length of the year is just an accident of where we happen to live. So that's not very interesting as a fundamental fact of nature. It's just, the sun is like the sun that takes this long to go around because, and we're here because this is a suitable environment. Um, so um, you could ask, well, what are civilizations likely to be like on
Mhm.
planets around other stars? At the moment, we have only one example.
Right.
So it has been argued that if civilization occurs on another planet around another star, it may be similar in some ways, even though all the details will be different. So, for instance, if you think civilization requires the ability to pick up things, and carry them around, then whatever is on another planet must have something like arms and legs and hands and feet.
Right.
If you think it needs an intelligence, then it needs something that does the equivalent of a nervous system to be able to represent information and keep it and communicate it. So, and then you say, well, what are the possibilities in biology? We don't know enough biochemistry to know whether the system of chlorophyll and other things the biochemists have discovered is the best system or the only system or only one of many.
Right.
So, but whatever it is, it's going to have similar function in the sense that it will need to convert starlight or sunlight into chemical energy that can support reproducing life forever. So the details would probably be different. The general structure might actually be similar.
Right. In this context, how do you see gravity as playing a role? Because changing gravity has clearly some impact on the way life forms grow, right?
Yeah, so it's a really interesting challenge. If the Earth were a lot larger, a lot more massive, then it probably would not have an ocean. It might have, or it would have a very deep atmosphere, and it might be hot under the atmosphere. So, of course, now that this has gotten to be an interesting subject because we have the chance to observe, then hundreds and hundreds of astronomers are predicting what might be like if there were another planet. But it does seem pretty clear that if a planet is at least twice the diameter of the Earth, then it's going to be very different from Earth.
Right. Right.
Another remarkable thing is, well, if the planet is much more massive than Earth, then space travel will become impossible for residents of such a planet, because the chemical energy that it takes to get off the surface is not available.
Right. Right. And again, in this context, tell me a bit about the Dragonfly, which you are involved in, which is apparently will be ready in 2034 to investigate the terrain to look for signs of life on Titan, one of Saturn's moons.
Yes, so I'm not really doing anything for it, but I like to tell people that it exists because it's such a remarkable accomplishment.
Right.
The Dragonfly is a little helicopter that will land on Titan. Titan is a satellite of Saturn, and it is unique among all the satellites because it has a lot of atmosphere. It's mostly nitrogen atmosphere, and it's enough to support a helicopter.
I see.
The gravity is lower, the density is higher, the temperature is very low. But Titan has lakes and rivers and rain and clouds and weather, and they're made of hydrocarbons instead of water. So it's a very interesting place to examine. We've already landed there once with the Huygens probe as part of the Cassini mission a long time ago now, so long ago I don't even remember. But we got pictures of the surface, we got ideas of what it's like, and we decided it's a really interesting place to go. So some of it's sort of abstract. Well, I'd just like to know about another wild and interesting place. Some of it is, at least for me, the possibility that if there could be life based on another system, besides liquid water as a solvent, then this is a place where nature has done the experiment. If there could be life based on liquid hydrocarbons at a low temperature, maybe there would be interesting organic molecules in the surface.
Right.
And it would certainly be very informative to find out.
It's fascinating. Just last couple of things, Doctor. You grew up on a dairy research center in New Jersey under a PhD father who had a research career in animal husbandry and statistics, and mother who was a teacher teaching French. How did you end up looking at the stars in a manner of speaking from a vantage point like that?
Well, that was what there was to do as a child in the countryside. I certainly was not going to be a farmer. That looked obviously very hard work. My dad already was doing animal studies of dairy cows, and his work was genetics, which is still a fascinating subject. He was already telling me when I was 6 years old, before the double helix was discovered, that we all have genes and chromosomes that control our fate in some mysterious way. And that got my attention. But at that time, there wasn't very much I could do with that. On the other hand, I could see the stars. And we visited the planetarium in New York City, and I heard the story about the planets and the stars, and it seemed so exciting to me. And then, as it happened, I got a chance to learn a lot more from books, and I got to go away to summer school and high school and study physics. And this was just such an exciting time.
Right. Your Nobel Prize citation talks of your discovery of the blackbody form and anisotropy of the cosmic microwave background. It's obviously very complicated. I understand some of it, but not all of it in great detail. For my general viewers, how would you describe the essence of what got you and Dr. Smoot the Nobel Prize?
Okay, well, two parts. Number one, the expanding universe picture says that the early universe was extremely hot and extremely dense. And that means that there was only one possible spectrum that it could have. It's called a blackbody spectrum at an extremely high temperature. Spectrum describes how bright is the radiation at each different wavelength. Then the expansion story says, as the universe expands, it cools, but it preserves its blackbody function. A blackbody is the ideal object that radiates and absorbs light perfectly. So its properties, therefore, have no effect on the curve, on the spectrum that we measure. So our job was to compare the measured sky with a perfectly good black body. So we built a little black plastic thing that emitted light as exactly like the cosmos as we could. So when we compared the sky with a piece of black plastic, we got the same answer.
I see.
Within hours, we knew that we had confirmed the story of the expanding universe.
I see. Yeah.
And a few years later, we got the precision down to 50 parts per million. So
really?
Totally astonishing, far beyond what we'd promised to be able to do. And so there's really no escape from the story of the expanding universe. And then that naturally leads on to, well, what could you do if you could measure even 1,000 times better? So there are things to do next, but they're not possible yet. The other thing that we did was we looked to see if the universe is equally bright in all directions, and it's not. We knew that it would not be, but we didn't really know how much. And so after you subtract all the local effects, like the fact that Earth is moving relative to the rest of the universe, we have a map of hot and cold spots. And this turns out to be very, very, very important, because if the universe were completely uniform and there were no hot and cold spots, then we would not be able to explain the formation of galaxies.
Right.
Something had to be there to seed the formation of a galaxy. Something had to be a little more dense than average so that it could stop the expansion of the universe locally and pull the matter back in and make a galaxy. So because of those hot and cold spots, plus the action of gravity, we are here.
Right.
Now we also know the pattern of spots is mostly determined by dark matter, which is currently thought to be cold material. So there's a direct evidence in the pattern of spots of something that you can't see, but you can deduce. That's the dark matter. There's evidence of the dark energy, the acceleration in the pattern of spots. There's even evidence of the number of neutrinos. We have lots of elementary particles, and neutrinos are little tiny massless particles, neutral particles.
Right.
And we already knew that there should be three kinds because of the way that they interact with other elementary particles. It turns out that it matters to the formation of the structure of the universe. And if there were more kinds of neutrinos, we would know
Right.
from the
Uh,
spots.
in this context, how do you see the recent discovery of the particle named Amaterasu after the Japanese belief system? It's been talked about quite a bit because it has pretty high EEV attached to it.
Remind me what the particle is supposed to be made of. Is this one of the composite particles with lots of gluons and quarks in it?
I'm not too sure. I spoke to one of the team members who recently published a paper in Science. They found it at the telescope array in Utah 2 years ago, and then it took them about a couple of years to go through the data and figure out that it was a single particle which they've named Amaterasu,
Oh,
which
that one.
splintered into, yeah,
Okay. So these, I guess we're talking here about particles that we receive on Earth from outer space.
right,
And so how do you find them?
right,
So the way that we do it, just for your readers to know, is we set up telescopes that capture the flash of light that happens when these particles come in. So an individual particle doesn't just come through, it crashes into the upper atmosphere and produces an immense cascade of billions and trillions of additional particles. So then when we see one of these events, we say, okay, it was not only immensely energetic, but we sometimes can tell where it came from.
right.
So if we get good enough at this, eventually we might say we know what object produced it.
Right. The
Now,
mystery here is that it came from what seems like a void. They've described it as an empty space. They don't know yet.
yeah, I did hear about that part. So to me, it's just a mystery, and we'll have to keep on working at that
Yeah.
one.
Just last two things before I let you go. Today happens to be the 122nd birth anniversary of Werner Heisenberg.
Oh my
Uh,
goodness! Yes.
I have a deliberately silly question in this memory, if you don't mind. What if his uncertainty principle also worked at the macro levels rather than just at the quantum levels?
Well, of course it does. It says that anything describable by a wave function is got an uncertainty about it. So there are plenty of things, quantum mechanical phenomena that have physical sizes that you can see. We just don't notice them. You produce them carefully in a laboratory.
How
Um,
about us?
well, everything about a human being is quantum mechanical.
There you
All,
go.
all of chemistry is quantum mechanics. Um, the structure of the atoms, the structure of the molecules is all controlled by the laws of quantum mechanics that tell how the electrons orbit around the nuclei
Right.
and how they combine. So our very existence is a proof of quantum mechanics.
Right. To conclude, Doctor, I always ask my physicist guest this question, quoting Dr. Steven Weinberg, who famously and somewhat controversially said, the more the universe seems comprehensible, it also seems pointless. I know as a physicist, you do not look at the universe in terms of its meaning or purpose or anything like that. But what do you think philosophically when you look at something this incomprehensibly big?
Well, I think if you're looking for purpose and meaning, you are in the shape of the atoms, you're looking in the wrong place. Um, there's a lovely new book by Stuart Kaufman called Beyond Physics, and you might enjoy talking with him sometime. He points out that the structures that we have are controlled by information. Your body, my body, they're controlled by the genetic codes and by everything that interprets the codes and everything around us. So everything in our world has a function. The cells have functions. They have little chemical cycles that have functions. So from beginning to end, the real world that we're in has purposes and functions everywhere. And if you're looking to see what are the atoms doing, you will never see it at the atomic level. But you can see it if you look for the functions and patterns of what's going on at the macro level.
Right.
So it's certainly true that you will not find purpose in individual atoms. You will find purpose in the structures that they create.
I see. Well, on that note, I want to really thank you for your time. I thoroughly enjoyed it. I hope you did some of it too. I hope you liked the conversation.
Yes. Thank you, Mayank. It's a pleasure to talk with you, and look forward to hearing more from you and with you.